This one is special. It has lots of info. There are many things you need to process. But if you're able to put all the pieces together and make a very clever observation, then you should be able to conclude the problem. I'll first make use of the hint as I try to collect all of my givens and see what my tool set for this problem is. So the derivative of tangent of x is sec squared of x. You can try to derive this from scratch, but at least for a problem like this, I don't think that's productive. You need to see it many times such that you remember it, not memorize it. So you do it multiple times so that you actually say, okay, I know that the derivative of tangent of x is sec squared of x because of this or because of that. Not because you memorized it. That's not the right way to move forward, at least. Okay. We want to find L. We have an expression for L. So that's amazing. Let's use this expression and see where it takes us. Hopefully it takes us far. Okay, so this is a normal integral. This, and that. What am I missing? dy by dx. Do I have it? Yes, it's right there. That's another piece of info I should probably utilize. So I would get... Maybe I should copy this first. Then I'll need a much longer... much longer... yeah. Oops. Let me just... Looks good. Actually looks bad. Maybe I'll just write it like this. I'll regret this waste of space. Okay, maybe I won't write down the square root. Or maybe I should. Okay, there you go. That's not so bad. So I'm squaring this thing. So it's safe to say I can cancel this out with that. When I cancel it out, I will have this expression. And now this is going to be without the square root. I have here a positive 1, here a negative 1. So probably these will cancel out after removing the square root. And now I'm taking the square root of this part. Maybe I should write it down. So here's what I mean. The 1 goes away with the 1, the square root goes away with the square. I need to take the square root of this thing. This should not be too difficult. I mean, everything here is is the power of 2. So this cancels out with the 2. Also cancels out with the 2 that's here. And this cancels out, becomes a 2. Now this is just simple, taking the radical and then everything works. So e to the minus x is on the outside. This becomes cosine squared. Then this is not too bad either. I have a cosine squared on the bottom and I have two expressions on top. One of them has a cosine. So probably I should divide these, right? So let me simplify this expression. Now all of this I'm just simplifying. I haven't even started integrating anything at all. I'm just simplifying stuff. So for the first term, I would get 1 over cosine squared, correct? And then I would take away from this, I would take away cosine x sine of x divided by cosine squared. Now, this is all being multiplied by e to the minus x. Let's not forget this. So we need to be careful. And we do this like this. We need to specify the brackets. Please. Yes, thank you. And so I've specified the brackets. 1 over cosine squared of x, I think I can write as sec squared of x. I hope that's okay. I hope that's not too much. And cosine squared and cosine, so the square goes away with this. I have a sine divided by a cosine. That's probably a tangent, no? Probably a tangent. Sec squared of x times the tangent of x times e to the minus. Maybe I'll go one step further. And instead of e to the x, e to the minus x, I'll write sec squared of x minus tan of x divided by e to the x. So we've utilized this fact. We've utilized also the fact that the line will be from 0 to 1. That's why we wrote 0 to 1. We still have not utilized this. So maybe I will do the following. Okay, this fraction is too long. Maybe I'll make it short. Do you agree with me that the fraction is too long? So to utilize this hint, here's what I would like to do. I would like to take the derivative that is right in front of me here, and I would replace it with the expression for sec squared. So that is just a simple substitution. Nothing too tedious, if you think about it. Then I have this, and I still don't know what the integral will be, what the value will be. So I have this setup where I have tangent of x, then the derivative of tangent of x, and then e to the x is on the bottom. Does this remind you of a very specific rule or formula? Maybe you need to think for a moment, just give it a good look. Give it a very good look and try to find the right setup for it. I personally had to take a look at it for some time to realize what we need to do here. It's a bit, tricky to see. But if you multiply by e to the x in the denominator and e to the x in the numerator, You multiply this by e to the x. Then this is nice, because in the denominator, e to the x times e to the x is e to the x squared. This reminds me a lot of the quotient rule. So you have squared here, and then e to the x is here, then the derivative of the upper term minus the upper term times the derivative of the lower term, which is e to the x. I mean, the derivative of e to the x is e to the x. So it's kind of doing it backwards. And if you do it backwards, this should be the derivative of tangent of x divided by e to the x. And probably you should check this yourself. I hope I tried so I try to motivate this as much as I can. I hope I was able to do so, because this is a bit difficult to see. We have an integral. Something is being taken the derivative of, and then it's the same thing but without the derivative. And then you're dividing by something. But then this something is very nice and it's very suitable, so that when you multiply by it here, you get the squared, as in the quotient formula, which tells you that the derivative of f over g is first divided by g squared, and then you get g f prime minus f g prime. So that the e to the x is so convenient, so that it is equal to its own derivative, and when you multiply it like this, the setup is so nice and it works. And that is just so cool, and it's so special, especially for this problem. So it's not something you would encounter normally, but it's a good idea, it's a good concept that you might utilize. I wouldn't really say that this is the type of questions that would show up on the exam, but it's the type of question which would teach you to try to learn some new ideas, some new interesting ideas. I think this is very interesting. You look at the reverse process. Yes, you know how to take the derivative of this, but do you know how to identify when you can construct a derivative of this function? So the inverse process, I think this is very important. It's also very interesting and unique. So that's why I kind of like this problem, even though it's a bit difficult and its style is a bit different. But then if you know this, then it's fine. So you can just plug in now. So you get tangent of 1 divided by e to the 1. Now tangent of 1 is the angle in radians for which the right angled triangle, the opposite side has the same ratio as the adjacent side. So when these two are equal, the ratio is 1. And when these two are equal and the ratio is 1, you have 45 degrees here, 45 degrees there. The tangent of 1 is 45 degrees. But we don't write it in degrees, we write it in radians. So 45 degrees is 180 degrees divided by 4. And 180 degrees is 1 pi radian. You get pi over 4 divided by e to the 1, which is e. I can write pi over 4e. And then I take away the case where I plug in 0, the tangent of 0, and e to the x. Not e to the x, actually e to the 0. E to the 0 is fine, it's 1. And if I remember correctly, the tangent of 0 is just it's just 0. This actually just cancels out. And I just made a mistake. So what I just computed is the tan inverse. Tan inverse of 1 is pi over 4. I think I mistook it because I did another exercise where you have the tan inverse and I explained the same thing. So tangent of 1 is just tangent of 1. That was an error from my side. Yeah, tangent of 1 is just tangent of 1. That is a good takeaway. But the tan inverse of 1 is pi over 4. That is for sure. But that is perhaps now not relevant for this exercise. And so to recap, we started with the formula that's here. We want to focus on utilizing all our givens. So we write down all our givens, including this. This is already given to us, and that is given to us. We want to find the length from 0 to 1. So we compute length from 0 to 1. Because our problem is from 0 to 1. And then you have dy by dx is given to you, so you plug this in. You make some simple simplifications. You know, the square root with the square, the minus 1 with the 1. You get this. You can simplify this part because there's a cosine squared and there's a cosine, so there's some potential. Divide this by that, you get x squared. Divide this by that, you get the tangent of x. E to the minus x is just dividing by e to the x. And then with a very clever observation and some insight about the quotient rule, if you make use of the last given which was not utilized and you write this down explicitly and just give it a good look, then you should be able, after some time, some finite number in time, finite number of intervals time, to find the solution. So this, in this case, would be the derivative of that function. And don't blame yourself if you're not able to find this. This is not an easy thing to do. But hopefully with the following exercises, now that you've seen it, you'll keep a good eye on examples that look like this.